Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky.
So imagine you are standing on a shoreline, but this isn't anywhere on Earth. The atmospheric pressure pressing against your suit is noticeably heavier, right? It's about 50% thicker than what you're used to.
Yeah, it would feel a bit like being at the bottom of a shallow pool, just from the air pressure alone.
Right, but at the exact same time, you feel almost weightless, and then a breeze brushes past you. It's barely a zephyr, maybe 2 or 3 miles per hour.
Which is nothing. On a beach here on Earth, a wind that light wouldn't even disrupt the surface tension of a tiny tide pool. You wouldn't even see a ripple.
Exactly. But as you look out at the liquid expanse in front of you, the physics just totally break down. You are watching these massive 10-foot-tall swells rolling toward the shore. And because of the gravitational mechanics at play, they're crashing in this, haunting, drawn-out slow motion.
It's such an incredible visual.
It really is. And you are standing on the shores of Krakenmare. It's the largest liquid body on Titan, which is Saturn's largest moon. And we're not just, making up a sci-fi scenario here. This specific visual is actually the mathematical key to solving one of the most perplexing planetary mysteries in our entire solar system.
It really is. It forces a complete recalibration of our intuitive understanding of fluid dynamics. We've had radar imagery of Titan from the Cassini mission for years now, right?
Yeah, mapping out all those crazy liquid networks.
Exactly. We've mapped these vast branching river networks that physically carve through the icy bedrock, and they just empty out into these massive lakes of liquid methane and ethane.
Yeah.
But here's the thing. Geologically speaking, when you have mature river networks feeding into a standing body of liquid, you expect to see deltas.
Right, like the Mississippi Delta or the Nile. You expect a bunch of mud and sand to just pile up.
Exactly. You expect to find massive alluvial fans of sediment deposited right at the mouths of those rivers.
Yeah.
But on Titan, the deltas are virtually non-existent. The rivers just hit the coastline and stop. It's a glaring anomaly.
And that anomaly brings us to what we're going to deep dive into today. We're looking at a brand new framework developed by researchers at the Massachusetts Institute of Technology, specifically in their Department of Earth, Atmospheric, and Planetary Sciences.
Yeah, lead author Una Schneck and Taylor Perron. They really cracked this open.
They did. They published this model called PlanetWaves in the Journal of Geophysical Research. Planets. And what's wild is they didn't set out to build some sci-fi wave simulator for fun. They built a rigorous mathematical tool to solve this exact geological discrepancy on Titan and, honestly, by extension, any planetary body with liquid.
Because waves are the engines of coastal erosion, the MIT team basically hypothesized that if Titan's coastal environments were volatile enough, the wave action would essentially act as a giant planetary sander. It would relentlessly obliterate any sediment deposits before a delta could ever even form.
Wow. So just wiping the slate clean constantly.
Exactly. But to prove that, they had to understand exactly how waves are generated in an environment that shares almost none of Earth's baseline variables.
Right, because previous attempts to model alien oceans usually just stopped at the most obvious variable, which is gravity.
Yeah, gravity is the simplest calculation.
And Titan has roughly 1/7 the gravitational pull of Earth. So less gravity means less downward force on the liquid, which means the liquid is easier to lift. But when I was looking at this, that single variable analysis completely falls apart when you actually look at momentum transfer, right?
Oh, absolutely.
Yeah.
If gravity was the only variable that mattered, a high-pressure atmosphere moving across a low-gravity liquid should theoretically just shear the surface right off. It would atomize it.
Like just turn the whole lake into a mist?
Right. So the model had to account for the liquid's actual composition.
And that is the huge critical advancement of the PlanetWaves model. It isolates and calculates this intricate dance between gravitational acceleration, atmospheric pressure, and the specific, the rheology of the liquid.
Yeah, its density, its kinematic viscosity, and its surface tension.
Right. And Andrew Ashton, a researcher at the Woods Hole Oceanographic Institution who collaborated on this, he framed the core math challenge around predicting what he calls the first puff.
I love that phrase, the first puff.
It's so descriptive. You have a completely quiescent, glassy, liquid surface. The model has to calculate the exact threshold of atmospheric kinetic energy required to overcome the liquid's internal cohesive forces and generate a capillary wave. Just a tiny ripple.
Because once that boundary layer is broken, the physics change entirely.
Tell me about that, because this transition is fascinating.
Well, once you get that first ripple, you introduce aerodynamic drag. The wind starts catching the windward side of that ripple, and it compounds the energy transfer. So it turns a tiny capillary wave into a full-scale gravity wave.
So the surface roughness increases, which basically allows the wind to get a grip on the liquid.
Exactly. The wind grips the water. But modeling that transition from a perfectly flat plane to a chaotic, turbulent swell that requires a flawless understanding of energy transfer coefficients. You can't just plug in the density of liquid methane and hope for the best.
No, you have to calibrate the math against a known, highly erratic system first.
Right, which is why the MIT team didn't start with Titan.
They started in our own backyard. They validated the PlanetWaves model using 20 years of continuous meteorological and oceanographic data from Lake Superior.
Which is perfect, because geologically speaking, Lake Superior operates as an inland ocean.
Yeah, it's massive. It has these huge fetch lengths, violent squalls, and then prolonged periods of absolute dead calm.
And the National Data Buoy Center maintains arrays all across Lake Superior. They provide high-frequency sampling of wave period, amplitude, wind shear stress, all of it.
And having 20 years of that data allows researchers to filter out all the statistical noise, right? Like rogue currents or localized thermal inversions.
Exactly. Atmospheric anomalies, all the weird outliers. They fed the PlanetWaves, model the historical wind velocity and atmospheric pressure for specific days. They locked in Earth's gravity and the density of fresh water, and then basically said, okay, model, predict the wave height and frequency for this specific Tuesday in 2008.
And it worked flawlessly. The model matched the buoy data perfectly. It accurately predicted the exact wind shear required to initiate those capillary waves and the subsequent growth into full-scale gravity waves.
It's an incredible proof of concept.
It really is. But this is where the concept of viscosity becomes the absolute linchpin. To kind of visualize this for you listening, think about it like this. If I have a wind tunnel and I blow a 10-knot wind over a basin of tap water, I get immediate ripples, right?
Instantly, yeah.
But if I swap that water for something really thick, like a bowl of thick honey or heavy syrup, that exact same 10-knot wind does practically nothing.
Right. The sheer stress isn't sufficient to overcome the syrup's resistance to being deformed.
Exactly. The physical effort required is vastly different. The momentum from the air mass just kind of slips over the top layer.
Yeah, the kinetic energy dissipates as microscopic heat rather than translating into actual wave motion. So, by proving that PlanetWaves could account for the specific viscosity and density of water on Earth using the Lake Superior data, the MIT team confirmed their math was rock solid.
Solid enough to handle the weird alien chemistry of liquid hydrocarbons?
Precisely. So we take this perfectly validated model and we point it back at Kraken-Meyer on Titan.
Let's really look at those parameters, because it is wild. The liquid is a cryogenic mixture of methane and ethane. It is sitting at roughly minus 290 degrees Fahrenheit.
So cold.
Unbelievably cold. And the density of liquid methane is about 422 kilograms per cubic meter. Compare that to Earth water, which is basically 1,000. So this Titan liquid is less than half as dense as the water we drink.
And then you have surface tension, which is incredibly low on Titan. Methane molecules don't have the strong hydrogen bonds that water molecules do.
Right, water likes to stick together.
Exactly. Water is cohesive, but the force holding the surface of a methane lake together is incredibly weak.
Okay, so then you factor in the gravity. We said earlier it's 0.14 grams, significantly lower than Earth. So the restoring force, meaning the gravity that's trying to pull a wave crust back down to make the surface flat again, is minimal.
But, and this is the kicker, you still have the atmosphere. Titan's atmosphere is mostly nitrogen, just like Earth's, but it's much colder and denser. It exerts about 1.5 bar of surface pressure.
Okay, so this is where I struggle with the visualization, and maybe you can help break this down. If the liquid is that light, right, and the surface tension is weak and the gravity is super low, but you have a dense, heavy atmosphere pushing across it, why does it form a cohesive 10-foot wave?
That is the big question.
Right, like why doesn't the atmospheric drag just rip the top layer of the methane off into a fine aerosol mist? I mean, if I take a high-pressure air hose and blast a puddle of gasoline, I don't get waves. I get a spray of vapor.
Yeah, it's a totally fair question. It comes down to a question of kinetic scale and atmospheric density. You aren't hitting the lake with a highly localized, high-velocity jet of air like from a hose.
Ah, okay.
The low wind speeds on Titan, remember that 2 to 3 mile-per-hour breeze we talk about? That means the dynamic pressure exerted by the wind is actually quite low, even though the atmosphere itself is dense.
So it's spreading the force out.
Exactly. The PlanetWaves calculations show that the wind transfers its momentum across a vast surface area. And it does this without ever exceeding the threshold where aerodynamic shear would rip the fluid apart.
Oh, wow. So it's almost gentle.
It is. In fact, the thick atmosphere actually acts as a stabilizing blanket. It presses down uniformly, maintaining the fluid phase of the methane while the wind slowly, steadily piles that light liquid up into a crest.
And because there's almost no gravity fighting that upward lift, the crest just keeps building and building.
Exactly. And that lack of gravitational restoring force is what dictates the whole kinematics of the wave. Think about Earth. On Earth, a 10-foot wave crest is incredibly heavy. Gravity pulls it down violently. That's what creates the rapid crashing turbulence we see when we go surfing.
Right, that classic crashing sound and foam.
But on Titan, the mass of that methane crest is very low, and the gravity pulling it down is very weak. So the acceleration of the falling fluid is drastically reduced. It literally takes longer for the methane to succumb to gravity.
Which creates that cinematic, suspended slow motion effect as it breaks against the shoreline. It's just so mind-bending.
It really is. And returning to the MIT team's original objective, this completely solves the mystery of the missing deltas.
Right, because a 2-mile-per-hour breeze on Earth does absolutely nothing to a shoreline. But a 2-mile-per-hour breeze on Titan generates a 10-foot slow-motion wall of liquid methane that is carrying a massive amount of kinetic energy.
Exactly. The river networks on Titan are undoubtedly carrying sediment down to the coasts. It's likely crushed water ice and hydrocarbon particulates. But the moment those rivers meet the lakes,
They just get hammered.
they get pulverized.
Yeah.
The relentless, easily generated wave action just destroys the deposits. The coastal erosion vastly outpaces the sediment deposition. So the deltas are being destroyed way faster than they can ever form.
It's just a perfect synthesis of fluid dynamics answering a planetary anomaly. It's so satisfying.
It really is. But, Titan represents a system that's in relative equilibrium today. The PlanetWaves model becomes even more revealing when we apply it chronologically to planetary bodies that have undergone massive changes over time.
Which brings us to a really fascinating part of this deep dive, ancient Mars.
Yes, the Noachian period of Mars.
Right, because Mars is effectively the ultimate control group for atmospheric degradation. If you look at orbital telemetry of Mars today, you see this dry, irradiated, dead desert. But the topography tells a completely different story.
We have undeniable geomorphological evidence of a hydrological cycle on ancient Mars.
Yeah, and the most famous example right now, the one everyone's looking at, is Jezero Crater. NASA's Perseverance rover is literally driving around in there right now precisely because it is an ancient paleo lake basin. And unlike Titan, Jezero Crater has a magnificent, beautifully preserved delta.
Which mathematically confirms something huge. It confirms that the wave action in Jezero Crater billions of years ago was not powerful enough to erode the sediment being deposited by the inflowing river.
Right. So the water was relatively calm, or at least the waves weren't Titan-sized monsters.
Exactly. But the conditions of that wave action were not static. They changed dramatically. During the Noachian period, which was roughly 4 billion years ago, Mars possessed a global magnetic field. It was generated by an active core, just like Earth's.
And that magnetic dynamo protected the atmosphere from the solar wind, which meant it could hold on to a thick atmosphere, which in turn allowed for liquid water to just sit on the surface.
Right. But then, the Martian core cooled. The magnetic dynamo failed, and the planet was suddenly exposed to continuous atmospheric sputtering.
The solar wind just started sandblasting the planet.
Exactly. It began stripping the upper atmosphere away, molecule by molecule.
And as that atmospheric envelope bled away into space, The pressure at the surface dropped. So the MIT team took the PlanetWaves model, locked in the gravity of Mars and the composition of liquid water, and they effectively ran the model backwards through time.
Tracking the wave dynamics as the atmosphere thinned out?
Yes.
Yeah.
And the dynamic pressure of wind is governed by a specific equation, right? Where pressure equals 1/2 the fluid density times the velocity squared. So if the atmospheric density drops, the wind velocity has to increase exponentially just to transfer the exact same amount of kinetic energy to the water.
Think about it like this. Wind is just moving air. It's molecules in motion. The mass of the air on Mars physically decreased over time. A 40-mile-per-hour wind in a thick atmosphere carries billions of tons of kinetic energy because of the sheer density of molecules impacting the water.
Right, there's just more physical stuff hitting the water.
Exactly. But a 40-mile-per-hour wind in a really thin atmosphere, it's mostly empty space. It exerts barely any physical shear stress.
So if you imagine setting up a time-lapse camera on the shores of Jezero Crater millions of years ago, the model basically illustrates a dying ocean. In the early days, regular seasonal weather patterns could whip up totally normal surface waves. But as the air literally thinned out over tens of millions of years, the exact same storms rolling in century after century.
The same wind velocity.
Yeah, the exact same speeds became increasingly impotent. The water was still there, the wind was still moving at 40 miles per hour, but the waves just started getting smaller and smaller.
It would require increasingly extreme, massive gales just to make a splash, let alone generate the baseline wave heights of previous eras.
Wow. You are literally watching the mechanical transfer of planetary energy just grind to a halt. The geological engine that powered coastal erosion on Mars slowly suffocated as the atmosphere vanished. By the time the lakes ultimately froze or evaporated away, their surfaces were likely completely stagnant no matter how fast the wind was blowing.
It's a pretty chilling visualization of planetary mortality, honestly.
It really is. So we've looked at Earth as the baseline. We've looked at Titan as the low-gravity alien chemistry extreme. And we've looked at Mars as the decaying atmosphere variable. But what I love about this research is that they didn't stop there.
Oh no, they pushed it way further.
To stress test the math, to make sure it wasn't just biased toward our local solar system physics, they pushed the parameters to the absolute terrifying extremes by applying planet waves to exoplanets.
Yeah, testing against extreme parameter spaces is vital if you want to confirm the integrity of a physical model.
Yeah.
You have to try and break it.
Right. So they modeled 3 entirely distinct classes of exoplanets. Let's start with LHS 140b.
This one has been heavily studied by the James Webb Space Telescope. It classifies as a super-Earth, and it orbits in the habitable zone of a red dwarf star.
It's a rocky world, roughly 1.7 times the radius of Earth, and its mass suggests it could easily host vast oceans of liquid water. But the gravity on LHS 1140b is immense.
Which creates an incredibly extreme environment for that restoring force we talked about earlier. When wind shear attempts to deform the surface of the water on this super-Earth, it is fighting a massive gravitational anchor.
The gravity is just pulling it down so hard.
Exactly. The kinetic energy required to lift a volume of water is drastically higher than on Earth. So the PlanetWaves calculations indicate that a windstorm that would generate, say, a 6-foot swell on Earth.
Like a really decent surfing wave.
Right. That exact same windstorm might only manage a turbulent chop of a few inches on this super-Earth. The water is effectively pinned to the ocean floor by gravity.
That is wild. And that introduces some really fascinating implications for oceanic circulation, doesn't it? Like thermal distribution on a planet like that. If you lack deep water wave propagation, the mixing of nutrients and heat might be severely stunted. The oceans might just be these heavily stratified, stagnant layers.
It completely changes how we think about habitability. But then they shifted from manipulating gravity to manipulating the fluid itself. The team analyzed Kepler 1649b.
Okay, so this one is terrestrial, roughly Earth-size, so the gravity is familiar. But astrobiologists theorize it operates as an exovenus, which means it likely possesses surface liquids composed not of water, but of sulfuric acid.
And the rheology of sulfuric acid is a completely different beast entirely. We know it's highly corrosive, obviously, but mechanically speaking, it is incredibly dense. It has a density of roughly 1,830 kilograms per cubic meter.
Which is nearly double that of liquid water.
Exactly. So even with Earth normal gravity, the sheer mass of the fluid requires intense aerodynamic drag just to initiate that very first capillary wave.
You're dealing with extreme fluid inertia. A standard Earth breeze simply lacks the physical momentum to overcome the density of the acid lakes. The wind would just flow right over the boundary layer with almost zero energy transfer.
It requires extreme, violent atmospheric velocities to generate any meaningful wave action on that planet.
Okay, but even that pales in comparison to the ultimate stress test. They applied the model to 55 Cancri.
This is the lava world.
Yes, the lava world. It's a tidally locked super-Earth orbiting so close to its host star that the dayside temperature exceeds 4,000 degrees Fahrenheit. The planet is literally covered in a global ocean of silicate magma.
Liquid rock. This pushes the PlanetWaves model to the absolute boundary of fluid mechanics. Because magma doesn't behave like a simple Newtonian fluid, like water or even methane.
How so?
Depending on the silica content and the temperature, magma often acts as a Bingham plastic.
A Bingham plastic, what does that mean in this context?
It means it has a yield stress, so it actually behaves like a solid until a specific threshold of shear stress is applied to it. Only when that threshold is met does it actually begin to flow like a liquid.
Oh, wow. So it's fighting the wind not just with weight, but with its fundamental state of matter.
Exactly, and the viscosity is just staggering. The internal friction resisting deformation is astronomically high. We are talking about a fluid that is incredibly dense, under higher than Earth gravity, with a viscosity millions of times thicker than water.
So the output of the MIT model for 55 Cancri is just profound in its starkness. To use an analogy here, it's like taking an industrial leaf blower, right, hurricane force wind, and pointing it directly at a swimming pool filled with wet, heavy, fast-drying cement. You're going to make a lot of noise, but you're barely going to move the surface.
That's the perfect way to visualize it. If you took a Category 5 hurricane-sustained winds of over 150 miles per hour, which on Earth is capable of generating 40-foot rogue waves, and you unleash that exact same aerodynamic force across the magma ocean of 55 Cancri.
The result is almost nothing.
Almost nothing. The model predicts waves of maybe a few centimeters in height. The immense kinetic energy of a hurricane is utterly neutralized by the rheological resistance of the liquid rock. The atmospheric drag is entirely insufficient to overcome the yield stress and the viscosity of the magma.
It's just incredible. It's a mathematical proof that aerodynamic force is highly conditional. It's the ultimate demonstration of boundary layer friction. The atmospheric molecules are colliding with the magma surface at 150 miles per hour, but the energy just dissipates as heat. The surface remains practically undisturbed.
Which is exactly why they ran this test. It validates that the MIT model isn't just calculating wind speed, it's calculating the total mechanical profile of the entire planetary environment.
Okay, so we've talked about the mind-bending physics, we've visited lava oceans and acid lakes, but practically speaking, why does this level of precision matter right now? Beyond solving geological curiosities like Titan's missing deltas, how are scientists actually using this knowledge today?
Well, it is fundamental to the engineering of future exploratory missions.
Right, because we are actively planning to send actual hardware to these environments. The proposed missions to Titan, for example, they don't just involve orbiters taking pictures from space. The goal is to deploy landers. Specifically, autonomous robotic vessels, space boats, essentially directly into Kraken Mare or Ligeia Mare.
We are literally conceptualizing extraterrestrial naval engineering.
Which is just the coolest phrase ever.
It really is. But if you are designing an aquatic probe for an alien ocean, the wave dynamics are the absolute most critical parameter for structural integrity. As Inishnek pointed out in the research, the probe has to actually survive the physical environment.
It can't just sink or get battered to pieces.
Right. And if the engineers assumed Titan's lakes behaved exactly like Earth's lakes simply because the wind speeds are low, they would severely underdesign the kinematic shock absorption of the hull.
Because even though the liquid methane is less dense than water, a 10-foot wave is still a 10-foot wave. And having that crash into an aluminum or titanium hull at minus 290 degrees Fahrenheit introduces terrifying mechanical stress.
Exactly. Materials become incredibly brittle at cryogenic temperatures. The cyclical loading of those massive slow-motion waves repeatedly slamming against the probe over and over, that could induce fatigue failure very, very quickly.
The boat would literally just crack apart.
It would. But now, because of the PlanetWaves model, it provides the exact wave height, the frequency, and the kinetic energy distribution that the probe will encounter based on the local meteorology.
So the engineers can use those specific parameters to design the buoyancy control, figure out the center of mass, and reinforce the structural resilience of the vessel. They can actually simulate the pitch and roll frequencies to ensure the communication antennas can maintain a lock on Earth or on the orbital relay, despite the high amplitude swells.
It's incredible foresight. We're using a mathematical equation validated by buoys bobbing up and down in Lake Superior to dictate the exact thickness of a titanium hull that will float in a sea of liquid methane a billion miles away.
It's the sheer audacity of human engineering. It requires a flawless grasp of universal physics. It proves that the mechanics governing the universe aren't localized just to our planet. The Navier-Stokes equations that dictate fluid motion apply just as rigidly to a lake of sulfuric acid on an exovenus as they do to a glass of tap water sitting on your kitchen counter. The only thing that changes are the inputs.
Which is really the core takeaway here. It strips away our anthropic bias.
Say more about that.
Well, we inherently view planetary mechanics through the lens of our own environment, right?
Right.
We assume water. We assume 1 atmosphere of pressure. We assume 9.8 meters per second squared of gravitational acceleration. That's all we know firsthand.
Right. It's our default setting.
But this research forces us to view Earth not as the baseline for reality, but simply as one specific coordinate on an infinite spectrum of physical variables.
And when you adjust those coordinates, when you tweak the density or dial down the gravity or strip away the atmosphere, the reality of the environment transforms radically. The next time you look at a puddle trembling in the wind or watch waves crash on a beach, realize you are watching a miraculous, invisible equation balancing Earth's exact gravity, air pressure, and water density. Just tweaking one of those numbers turns our familiar world into a completely alien landscape.
Completely changes how you look at the natural world.
It really does. The interaction between moving gas and standing liquid is the primary geological sculptor of coastlines across the cosmos. And knowing that the mechanics of erosion operate at completely different extremes depending on the rheology of the local fluids leaves us with a pretty profound final thought.
Oh, definitely.
If the slow-motion methane waves of Titan can erase vast river deltas, and the dense, viscous oceans of other worlds remain completely undisturbed by hurricane-force winds, we really have to consider the unimaginable geomorphologies waiting out there in the deep universe. What intricate, bizarre coastal architectures, cliffs carved from exotic ices, or abyssal trenches hollowed out by heavy acidic tides have been sculpted over billions of years, they are out there right now, operating under a set of physical rules we are only just beginning to mathematically comprehend, just waiting to be discovered.